Hello, I'm Orion Sauter, and I'm a researcher in the LIGO collaboration, which studies gravitational wave astronomy. We've been able to learn an enormous amount about the universe from traditional astronomy, but certain objects, like black holes, allow only indirect measurements using electromagnetic waves, or light. As the name suggests, black holes emit no detectable amount of light, so until recently the only way to observe them was indirect, when their large mass would cause a nearby object to change its course, or when they obscured the light from something behind them. A little over 100 years ago, Einstein published his general theory of relativity, which is currently our best description of gravity. The theory states that mass bends space around it. And I like to imagine a bowling ball on a trampoline. This is a miniature version that we use in our demo lab to show this effect. So you can imagine that the heavier the bowling ball, the more it would stretch the surface around it. And if you rolled a smaller ball past it, it would deflect the path or even orbit around it. And that is exactly how the moon orbits the Earth. So here you see the Earth stretching out a bit of space around it, and you could imagine rolling the moon past it, and it would get caught in this dip and revolve around the Earth. After formulating the equations behind general relativity, Einstein realized they predicted the existence of gravitational waves, distortions in space that propagate outward from certain objects. As these waves move through space, they compress it in one direction while stretching it in the other. LIGO is built to observe these waves. The detector consists of a pair of arms in an L shape, each about 2.5 miles long, and it's able to sense the changes in length caused by a passing gravitational wave. We currently have 2 of these detectors operating, one in Hanford, Washington, and the other in Livingston, Louisiana. I can show you a picture of the Hanford Observatory here. So there you see the 2 arms that I described. And we've had to put an enormous amount of engineering labor into getting rid of any sources of noise. So we've got very sensitive seismic detectors that allow us to cancel out even the noise of passing traffic can set off the detector. And so we need these seismic isolators to be able to cancel that out. On September 14th of 2015, we made the first ever direct detection of gravitational waves, which were produced by a pair of black holes spiraling in and colliding. We had just completed upgrades to the detector when this exceptionally loud signal arrived after a journey of over 1 billion light years. The 2.5-mile arms I described earlier were stretched by less than the width of an atom, but we still caught it. I can show you a simulation of what that collision looked like up close. So here you see the 2 black holes spiraling around each other with a field of stars in the background, and you can see the distortions in space that they're causing as they move around. As they get closer, they also speed up, and that's a higher frequency wave that they emit and also a more powerful wave. And then they finally merge, but still have a little bit of energy that they have to shake off before the space completely smooths out again. My project, called Flux, searches for waves from pulsars, which are densely packed spheres of subatomic particles. 1 teaspoon of neutron star material would weigh 10 million tons. Unlike the black hole collision I just showed, waves from neutron stars are much weaker but last for years, so we can add up the signal over time. The era of gravitational wave astronomy has only just begun, and already we're gathering valuable information about the universe. It will be exciting to see what else we can find. Thanks for watching.